So now we can use stoichiometry, and we can use solution stoichiometry and the unit of molarity, which is moles per liter, and we can find out concentrations of an unknown solution. And by the way, this is what you'll be doing in experiment 12 next week. This technique is basically called titrations. Titration is when you add a known concentration of a solution to an unknown concentration to figure it out. And typically it involves a neutralization reaction where we add a base that we standardize. We know its concentration to an unknown acid to figure out the acid's concentration. And we use stoichiometry to get it. So what does it look like? Well, in here, I have my sodium hydroxide. And they're just showing it as this right here are just little OH minuses, because they're showing that the hydroxide is really what's reacting and the sodium is just a spectator. And then inside the water, I have a bunch of acid, H pluses, right? So I know the concentration of my base, but I want to know the concentration of that. I want to know how many moles per liter. And I could start by, well, I know there's 10 mils in here. So I just need to know how many moles. Well, I keep adding my base until it fully reacts with all the acid. And when there's no more acid for the hydroxide to react with, it's called the equivalence point. And in the titration, you actually go one drop beyond, because when the hydroxide has no more acid to react with, it'll react with the indicator and it'll turn it a light pink. And that's typically referred to as the end point. So a lot of people say the equivalence point and the end point are the same thing. They're not. The equivalence point is where I have a 1 mole to 1 mole ratio between the protons and the hydroxides. The end point is I go 1 drop over with the hydroxide, and it reacts with the indicator because there's no more acid left, and it turns a light pink. But you need something to tell you that the reaction is done. So when it turns light pink, I can determine from my initial volume and my final volume, remember delta V, the volume of my sodium hydroxide I added. And from the volume I added, so from the milliliters of sodium hydroxide, I can convert milliliters to liters. And once I have liters, I can go from liters to moles of sodium hydroxide. And then I can use my mole ratio, let's say 1 mole of sodium hydroxide to 1 mole of HCl. Let's say this unknown acid was HCl. I can then get my moles of HCl using stoichiometry, plug it in here to get my molarity, because I know I started with 10 mils. So the indicator basically tells you when to stop. It's called the end point. The equivalence point is where the moles of acid and base are the same. So we can calculate the unknown because we're going to use the volume of whatever we add of the known to figure out how many moles of known we added. And then we can use our balanced chemical equation and our mole ratios to figure out the moles of unknown, and then divide it by the volume of the sample. So it's kind of like, you know, basically a stoichiometry problem, right? So this is good review for chapter 13 and the test, right? So calculate the milliliters of a 2 molar sulfuric acid solution required to neutralize 50 mils of a 1 molar potassium hydroxide. So what do I want? Mils of H2SO4. So what am I given? Now, a lot of people get confused. They're like, there's 3 things given. Okay, but realize I want H2SO4. That's my unknown. That's not really my given. So my given must be something with KOH. And I have to figure out, what number do I use? Do I use the 50 mils of KOH or the 1 molar of KOH? Well, the way you can figure this out is the molar is a mole. It's basically a ratio. It's 1 mole of potassium hydroxide per 1 liter. So this is a ratio. And milliliters is not a ratio. So if I don't end with the ratio, I shouldn't start with a ratio. So really, I should start with the 50 mils. So I can say, well, 50 mils of my KOH, there's 1,000 mils in 1 liter. And in 1 liter of my KOH, I see right here, there's 1 mole of potassium hydroxide. And now I can use my mole ratio. There's 2 moles of potassium hydroxide per 1 mole of H2SO4, right? Now, if I was given volume of H2SO4 and I wanted to figure out molarity, I'd be done. I take the moles of H2SO4 and I plug it in there and I divide by the mils. But in this problem, I know the molarity and I want to know mils. So now I have to keep going. How many moles of H2SO4 per liter? Well, that's what this tells me. There's 2 moles of H2SO4 because whenever you see big M, it's a ratio per 1 liter. And in 1 liter, there's 1,000 mils. And then you get your volume of H2SO4 that you neutralized. And it's 12.5 mils. So this is kind of a review of solution stoichiometry. The difference from chapter 13 and 14 is 14 really emphasizes neutralization reactions and not all solution stoichiometry. So here's another example. The titration of 10 mils of an HCl solution, right, of an unknown concentration requires 12.54 mils of a 1 molar NaOH. What is the concentration of HCl? So this is what you'll be doing in lab next week. I want the molarity of HCl. What is molarity?
Moles per liter.
Yes, it's moles of HCl per liter. Now, I already have mils. I could easily convert that to liters. In fact, I'll just do that right now. I'll just say 10 mils is 0.011 or 100 liters. So the only thing I have left is to solve for what? Moles of HCl. How am I going to do that? Stoichiometry. I'm given 12.54 mils of a 0.1 molar sodium hydroxide solution, reacted that and neutralized it. So what do I need for stoich? I need, what was rule number 1?
Balance equation.
Yeah, and this time they didn't give it to you. Why? Well, because we've been doing this so much, you need to know that, right? So HCl is my acid. Sodium hydroxide is my base, and I get 1 mole of water and 1 mole of sodium chloride. So now I have my ratio. It's 1 to 1. So I start with 12.54 mils of sodium hydroxide, and there's 1,000 mils in 1 liter. And in 1 liter of the sodium hydroxide, that's what this gives me, 0.100 moles of sodium hydroxide. And we're lucky, this is easy. This is a 1 mole to 1 mole relationship for HCl. I'll get that value, let's just say X, and then I'll divide it by what we did here, the 0.01000 liters. Now, some students do this, and I actually, in 200, always encourage students to do this. If you guys don't want to do that, that's fine. Some students just go 1 divided by liters. And what will happen is the mils will cancel the liters, the moles of NaOH, and then the moles of HCl is what you want. And you divide it by the liters of the HCl. So you can do it that way. Or you can just solve for moles and plug it into that quotient. So there's a balanced equation. And the work, let me, sorry, I wrote that all out. I like writing it out for you. But the work, and you see they in this problem, they did a shortcut, right? So they went 12.54, and they just said, oh, actually, they didn't do it. You could say 1,000 mils is, you know, the same as a liter and just kind of eliminate that. But 1 liter, and then 1 liter is the 0.1 moles, and then we get the moles of the HCl. And then we divide it by the 0.010 liters. And we get our concentration. And why is it 3 sig figs? I have 4 sig figs here. I have 4 sig figs here, but this is only 3. Why? Leading zeros never count. Trailing zeros count if there's a decimal. So I get 3 sig figs and a 0.125 molar. Now, a lot of students, there's a cheat. There's a cheat for this, and I don't even want to bring it up because it's not a good cheat. It's a formula that we use for dilutions, but that won't work if it's not a 1 to 1 mole ratio. So I always tell students, I'm not going to even tell you the cheat, even though I did, because if you use it, just be aware that I know it's a cheat, and on the exam, I'm probably not going to have a 1 to 1 mole ratio, right? That way you can't do the cheat, and you actually have to do the stoic.